Rob 201, excuse me. I was right. Then there were 4. Okay, so last time we were looking at very careful definition of continuity, and its big payoff was the ability to take limits inside of functions. And what it says is if f of y is continuous at y0, where y0 is the limit of g of x as x goes to x0, then you can take the limit inside. And it just simplifies everything. And with that method, you can compute this derivative, well, it is a derivative, but this limit here, the limit as h goes to 0 of e to the h minus 1 over h is equal to 1. The derivation is given at the end of notes from Wednesday of last week. Okay, so that completed chapter 4. We're moving on to chapter 5, differentiation. And we're going to cover two valid means to define the derivative, each useful. One derivation is the traditional local slope. Otherwise known as rise over run. And the other method is local linear approximations. And I'm going to emphasize the second, even when we're doing derivatives of scalar valued functions that only depend upon a single variable, the classic Math 115 material. Because when we start doing Jacobians and gradients, which are derivatives applied to vector valued function depending upon several variables, the linear approximation picture makes the notion of a derivative a little bit easier to grasp, in my opinion. Okay, so let's just do a little bit of the rise over run. Oh, come on. We probably don't need it quite that large. Okay. Can you guys see clearly all the notation on here? Okay, so we've got a function f of x. We have a point x0. We have that point perturbed by h greater than 0, and that distance we're calling delta x. So that's the run. And then the rise is the change in the function values from f of x0 to f of x0 plus h. So this line, when you pass it between 2 points like we've done over there, that's called a secant. And secant just means cutting in Latin. So it's just a Latin phrase that means cutting. So it's a line that cuts the curve here in 2 places. And you can see as we take the h smaller and smaller, that eventually it is converging to a line that is tangent to the curve at the point x0. And so that's the df by dx at x0, the limiting curve as h goes to 0. So we take rise over run. As the run goes to 0, we're going to use that to define the derivative at the point x0. Okay, so this is like we were doing with integration. The delta f's and delta x's go to df's and dx, which denote infinitesimal variations, whereas the deltas are non-zero variations. And then we have limit as h goes to 0. It's a double-sided limit. F of x0 plus h. So there's the rise. Then the run is literally x0 plus h minus x0. Then, of course, these guys cancel. And so we just end up with limit h goes to 0, f of x0 plus h, so increment in the x direction. There's the rise, and then the run is h. So if the limit exists, the derivative exists. If the limit doesn't exist, the derivative doesn't exist. Simple. It's simpler than keeping this mic on. How about that? Yeah, so that's about all to say about that. And it is a double-sided limit, so you need the limit from the left and the right, both existing and both having the same value. So that's what that means. So let's just get down and do a few. So we'll take f of x as x squared, and we'll take a point x0, an element of R, arbitrary. So then what is its derivative at the point x0? So the first thing we do is we write down the definition. So that's actually a definition. And we plug in for our function. And so this is x0 plus h squared minus x0 squared over h. Copy our limit down, and then we just expand it out. So x0 squared plus 2x0h plus h squared minus x0 squared all over h. So this is calculus. This is algebra, and this is the typical grind of calculus, more algebra. These guys cancel, giving us more algebra. So we end up with 2x0h plus h squared over h. algebra, then divide h into top and the bottom, and this is the limit we have to evaluate. Okay, so the h cancels here, and then the h squared divided by h leaves h. Yeah, it's kind of sad. After all that work on the limits from the left and limits from the right and everything, that's our first limit to compute for a derivative. It's a little bit, I don't know, disappointing that it's so easy of a limit. It should at least be a little bit more challenging, but it's not. Okay, so maybe that's good. So at a general point, we typically write it like this. So d by dx of x squared is just 2 times x. Okay, so that's the local slope. Okay, so if that's A, then this is B. Any questions on that, or is it straightforward algebra and stuff? Okay. The limit wasn't hard at the end. It was just all the algebra. But we did do a limit, but that wasn't too hard. Let's take f of x equals e to the x. And this time, let's leave x as a variable, which is what many of you are probably used to doing. Hopefully next semester I get many more students who are just learning the joys of calculus. And so d by dx of e to power x equals limit h goes to 0. We plug in f of x plus h, so that's e to the x plus h. We subtract f of x, we divide by h. So that's the definition. So we just applied the definition. Well, what we can do to simplify this limit is use our exponential rules. So this is limit h goes to 0. We factor out e to the x. That leaves e to the h minus 1 over h. So that's more algebra. E to the x doesn't depend upon h, so we can just take it completely outside of the limit. It's a constant in this limit calculation. And then that leaves us e to the h minus 1 over h. And we know the value from what we started with in the summary, which you were given as a homework assignment with hints, and it's also solved at the end of Wednesday's lecture. Come on, go away. Okay, so this limit is 1, and so this just equals e to the x. So very nice. D by dx, e to the x equals e to the x. Let's get all the monomials in one fell swoop. F of x equals x to the k. K equals 1, 2, 3, dot, dot, dot. So then d by dx of x to power k is by definition equal to limit h goes to 0, and we plug in the function evaluated at x plus h. So x plus h, all that raised to power k, minus x to power k, the function at x, and divide by h. So once again, That's just the definition. Okay, so how do you expand out monomials? Anybody remember a theorem that's worthwhile on this? Binomial theorem. That's the right bid, okay? So if you're rusty on it, it's covered in the pre-calculus chapter 1. Let's limit. H goes to 0, and we need a little bit extra room this time. So this becomes, the leading term is x to power k. The next term is kx times h. Excuse me. They've all got to add up to k. So this will be x to the k minus 1, times h. And then there's all of the other terms. Sum k equals 2. Can't use k. Got to use a different index. I is 1 to k. And we have the binomial coefficient k choose I, x to power k minus I times h to the I. So that product always has power k distributed, and then we still have to subtract off the x to the k. This and this cancel. So we'll rewrite our limit. And so this is kx to k minus 1 h. Summation I equals 2 to k and then this limit becomes very easy to evaluate as well. This one and this one will cancel, so this constant k x to the k minus 1 remains. And then the lowest power of h here is 2, and so this always has an h in it when we divide by h, and hence all of those terms go to 0. Okay, so equals kx to the k minus 1 plus and then something that goes to 0. And this will be the sum I equals 2 to k, binomial coefficients, we don't care what they are, x to k minus 1, h to I minus 1. And because I starts at 2, there's always an h and it goes up, and so this limit is 0. And so the answer is d by dx, x to power k. The coefficient comes down, as you guys remember, x, and then you subtract 1 from the exponent. Okay, and our friend here indeed was the binomial theorem. Whoops. You didn't reach, okay. And this was binomial theorem. Okay, so it's a handy way to deal with powers of two quantities, a sum of two quantities, and that's why it's called a binomial, because it's got two terms in it. Anybody want to calculate more derivatives, or is that enough? Enough? Yeah, okay. Very good. Let's do a few non-examples. Okay, so we just did a bunch of functions that are differentiable. Let's see when things go south. So when I'm understanding a new area, I try to understand, okay, this works under this hypothesis, and if I break one of them, here are counterexamples. It helps me understand the limits of what I'm working on. So let's ask this question. Is f of x equals absolute value of x differentiable at the origin? Okay, so there's our function. Well, that slope is +1, and this slope is -1, so it's not looking very good, right? Because the derivatives, the limits, the slopes need to be equal at the point. So, yeah, not looking good. So our intuition is that when something has a kink in it, I think that word was used last week, it's unlikely to be differentiable. So how do we actually show that? So this is where it's worth taking the limits from the left and from the right. So we're taking x0 equals 0. When h is positive, f of 0 plus h is just h. So this is the limit. H goes to 0 plus of h minus 0 over h. And I think we have not too much problem recognizing that the h's cancel, the 0 doesn't play a role, and we just get 1. And then we will slyly take the limit from the other side, which is also part of the definition, because it's a double-sided limit, so left and right have to be equal. So this is how we formally show that there's an issue here. Okay, so when h is negative, what is the absolute value of h? So I'm working with h's over here. This is the absolute value, okay? So this becomes minus h minus 0 over h, and it's because we're taking limits from the left of 0. And that's the definition of the absolute value. And so minus h divided by h, this yields minus 1. Okay, so left and right limits both exist. That's great, but they don't agree. Okay, and that's going to happen when we have kinks like that. So a bend, right angle, 30-degree angle, any kind of angle is going to be a problem. Okay. Now let's just note that the function is differentiable at all other points. Okay, so we're saying the function is not differentiable at the origin, but if I'm just picking some random point here and looking at slope information, it's very nicely defined. It's just a line, so there's no issues there. Does that work for everyone? Okay, so let me have you think about this one then. F of x equals 1 plus x when x is positive, and x when x is less than or equal to 0. And we're going to take, once again, x0 is the origin. What does it look like? There's one side of it. There's the other side, parallel. This is excluded, and this is, whoops, this one is in the wrong spot. This is in the wrong spot. You guys were being too nice to me. Okay, so that's what the function looks like. Is it differentiable at the origin? What's your intuition? This is yes, this is no. We like no's, okay? Okay, but what's the reason? How do we use our definition to show that it doesn't work? So you know intuitively it's not, which is great, okay? That's all you need as an engineer. Now if you go into Math 217 or Math 351 or Math 451, by nose is not good enough, okay? You got to do a little bit more. So let's try one of the single-sided limits. Okay, start with the definition. It's always a good policy on homework in all engineering classes when there's math. That way you can at least get partial credit for properly inserting the definition in there, okay? So f at 0 plus h, okay, so this is what we're going to be looking at. So it's the limit as h goes to 0 from the right. Well, from the right, the function is equal to 1 plus h. At the origin, it's equal to 0. And that's the issue. We end up with h over h, that's 1, but then we have the 1 over 1 plus h. So that's plus infinity. Okay, does that make sense to us that that's plus infinity? Yes. The slope to go from here to here is straight up, so it's infinitely steep, okay? It's infinitely steep, so that's how you can double check your intuition. Okay, so I'm going to abbreviate differentiable at the origin. Okay, so these counterexamples are all part of a kind of a general fact here. It's really one fact, but I'm going to write it in two different ways. If f is discontinuous at x0, then f is not differentiable at x0. Not. So discontinuous gives us not differentiable. So that's this picture. Okay? The function has a jump at the origin, so it's not continuous, it's discontinuous at the origins. So you don't have to do any calculations, okay? So it's just a fact. And whenever you have a jump, you will do one of these limits and you'll always get plus or minus infinity. Now the origin here, the function is continuous. So this wouldn't apply. Now I'm going to rewrite this and say the same thing. If f is differentiable at x0, then f is continuous at x0. So is differentiable is continuous. Okay, so why are those two things the equivalent? You're probably familiar in logic that if you have A implies B, that is equivalent to not B implies not A. Okay. Logical negation. Yeah, I know. If you're a veteran of EECS 203, and you don't know that, you're not going to get very far in the course. Okay, but whatever you're doing, sometimes it's better to think about it in the negative, or it's nice to think about it in the positive. So, hey, clearly the slope is very nice here, and the function is continuous, okay. Function has a jump there, it's discontinuous. I don't have to do this limit calculation to check differentiability. It's automatically not differentiable. So it just kind of speeds up calculations, that's all. And if you want to see the formal proof, it's in the textbook, but I don't think it's super interesting, to be honest with you. Okay, so there's actually three different notations that are used with derivatives. We're going to introduce a second one now. So we have one, which is the little d f, infinitesimal increment f over little dx, little infinitesimal run. So we have 1 df by dx at x zeros by definition equal to limit h goes to 0. So the rise over run. This is due to Leibniz, and that'll be important to us in just a little bit, but right now you don't care who really did it, okay? Maybe you remembered, maybe you don't. Doesn't really matter. But in a video we're going to watch in a little bit, it'll be helpful to remember it's from him. And then there's this prime notation, which means exactly the same thing. Since I left off the x0, I'll write it like this. And this is due to Lagrange, as in Lagrange multipliers, Lagrangian dynamics, etc. And there'll be a third one that we'll use when we do differential equations. That's due to Newton. Okay, so that's how you do the first derivatives. Second derivatives. So we use d2 f of x, and then the 2 there for the squared. And that's by definition d by dx applied to df of x. And then f double prime of x is by definition equal to f prime of x prime. So these are derivatives of derivatives. So why is this important? It's emphasizing that even though we think of differentiation, let's go back to our picture, as being something that's happening at a point where we get this local slope, it's important to realize that as we vary that point, we get different local slopes, and so we're creating a new function. So at each point, we're assigning a number, which is the slope, and that's the derivative. Okay, so d by dx takes functions into functions, unless you evaluate it at a particular point. So if you leave x free as a variable, differentiation is an operator on functions that gives you new functions. And then the nth derivative dn f of x dx to the n is by definition equal to, so it's recursive. This will be the n minus first derivative and then the other one, we stop writing we stop writing primes. And this is by definition equal to the n minus first derivative. And then we do prime of that. Okay, so that's, and this notation, df by dx, personally, we're going to do something called the chain rule. It's much easier using this notation. But deriving all of those differentiation rules, this is much easier. It's kind of strange that just one notation will change, will make derivations easier, but it does. Where'd you go? There you go. So this is pretty much the only derivatives that are worth memorizing. So just as you'd feel kind of silly if you had to look up 9 times 7, okay? You don't need to memorize it, you got a calculator, okay? But you'd feel kind of silly if you had to look it up. You will look kind of silly as an engineer if you don't know the derivatives in this table. And if you want to add a few others, arc sine and arc cosine, yeah, we'll show you a little bit later how to derive them. But that's about it. That's about it. That and a few rules for calculating derivatives of complicated functions from simpler functions. Okay, so now what do you do when you have a really interesting function? So here I'm just reminding you, how do you get the code examples from the book? Okay, you go over to the pages on the side here that's highlighted. You just click on pages, then you do, this will come up, you do code from textbook, and then we're in chapter 5. Yep. Vocarium for me does the same thing for you. You get the little spinning arrow and stuff. Okay, we're in chapter 5. Don't worry, I've got it open and already runs. We're not going to be dealing with it slow. And then there's a part 1, which is all of the code in the book chapter, most of it. And then there's one called demos. And so let's skip to the part 2 demos. Okay, so as an engineer, doing all your calculations by hand does not leave good documentation. It's much better to do it in code. Now, these Jupyter notebooks are a very convenient way to document it, but you can just use any tool that will allow you to output it as either text or LaTeX or some format and paste it in. So even though you have memorized your multiplication table, when you expand that to doing numbers that have 3 or 4 digits, you still do things by hand every once in a while, but mainly you check them. When you do derivatives, you mainly want to check them and document them for your colleagues, okay? So Julia has nice tools, and I've also shared with you Wolfram Alpha Pro. So I don't know if everybody activated their license yet. It's good for 1 year. So if it's in your spam, go find it. We'll use it more when we get to antiderivatives, but you can use it for derivatives. The cool thing of Wolfram Alpha Pro is it gives you every step in a derivation, okay? Whereas Julia just gives you the answer here. So here we're using the symbolic toolbox. Symbolics is the native symbolic manipulation toolbox in Julia. You see there on line 4, commented out, using SymPy. SymPy is a symbolic toolbox developed for Python. The pi is for Python. And SymPy is a Julia front end into the Python thing. Now, for better or for worse, there's much more use of Python in the world thanks to machine learning, and so the symbolic toolbox is more developed in Python. Symbolics is a little bit easier to use, so you can use either one you want. The calling of it, is kind of awkward when you've got to say differential of x of f, like it is on line 9 here. It's a little bit awkward. So what I do is I just create a function. I'm calling this one deriv. If you want to call it diff, feel free, okay? And then since we're using the symbolic toolbox, we create a symbolic variable x, like in line 13. You can create arbitrarily complicated functions and then just start differentiating away. And that's a lot nicer than doing it by hand, okay? If you want to take that function and evaluate it at a point, I think this evaluate function I've written here on lines 2 through 4 is quite convenient. Using dictionaries and replacing the variable x with another variable x0, which is typically a number, and getting the number out is a little bit awkward notation to keep typing. But, okay. And then when you do things in the symbolic toolbox, Julia is heavily typed. MATLAB is hardly typed at all. Python is reasonably typed, okay? Julia is heavily typed to help avoid conflicts of variables showing up in different ways, and the type in the symbolic toolbox is num for, I don't know, numeric after you've evaluated it? I don't know. I guess it's calling it a numeric, but it's not a real number. When you differentiate things, it doesn't always simplify them, okay? So you can help yourself. So here's an example where there are cosine squareds and sine squareds. You can see the 2 cosine squared and the sine squared and things, that those can be combined. And it doesn't always catch them. So I'm going to show you how to do that. Another thing that's useful is it's very easy in Julia to turn math into LaTeX if you want to stick it into a report. So you just use the LaTeXify package, and then you can output things. It's not beautiful. Sometimes you can notice that the exponents have 2.0, and we typically don't write x to the 2.0, x to the 2.1 when it's correct, okay? So you might have to do a little bit of hand correction there. And then this is just showing you how you can simplify answers and have simple algebra like cosine squared plus sine squared equals 1 be applied, and then you can do that. So what I've done here is just show that you can actually iterate derivatives. All I did was write a for loop in lines 5 through 7, that's calculating the derivative each time it goes through, and I've got it on line 3 set to go through 5 times, okay? So just, and then you want to calculate the 5th derivative, bingo. And yep, probably didn't want to do that by hand, okay? And then this is using a slower version of the derivative where the simplify command is being applied. So the cost is time, but you get a cleaner answer, and the sine squareds plus cosine squareds have been canceled. Okay, so you just need to go through and play with those yourself a little bit. If in the end you're getting functions and all you really want to do is evaluate them at points, and you would like them to be real numbers when you evaluate them and not this crazy numeric type that comes out of this symbolic package, I find numdiff and finite diff to be really great for that. Okay, so they have a very simple calling sequence. I've changed the function name here to G, and I'm doing finite difference, okay, and calculating the derivative. If I were using this very much, I would encapsulate that into simply a n diff or something function name that's much easier than this one, okay? In Julia, you can have many packages uploaded. So in line 6, where it says finite diff dot, and we're using package finite diff, it's just saying if there's another package that happens to call derivatives by using finite underscore difference underscore derivative, use the one that's in the package finite diff. That's what it's for, okay? So it helps you specify the package. And that's important because personally, I use mostly forward diff now that I've gotten to know about both of them. And you can see the forward diff dot derivative here, and the dot, forward diff dot is just to say it's use the derivative tools inside the forward diff package and not the other one. Okay. And that's all I wanted to show there. Okay, so as real engineers, these are the tools you use. Wolfram Alpha Pro. Now the large language models are pretty good, and you use things like this, okay? So it's only in your toy homework problems in your engineering courses that you will do it by hand. And then the one that you don't want to do by hand, that's on the final exam, of course, okay? That's just the way life works. So we'll take a break here and start back up in 5 minutes, so 5:28 or something. Cool. It's not time to start, so this is just me talking, but so in the textbook, I go through another method of calculating derivatives called automatic differentiation. And this is differentiation meets databases is really what it is. And it's a very efficient way to keep track of all of the terms that tend to get generated when you start doing derivatives. And all of the backpropagation gradient descent algorithms in the AI models, they're using automatic differentiation to carry that out, okay? So it's something good to know about. It's not convenient much for humans when you're doing homework-like things. It's not that great for that. But when you're coding up some big project from a class and you would like to be fast, accurate, yeah, automatic differentiation is a way to go. And there's even versions of it where it'll differentiate an algorithm for you. So not just a function, you've got not just what we normally think of as a function as humans writing down 2 lines or something like that, but you take a function from a program and you can actually differentiate its output with respect to certain variables, which is very convenient, okay? Very convenient, whereas I would only do it by hand coding a numerical approximation of the derivative, but they have ways to go in there and start extracting them automatically. So that's kind of cool stuff to know about. You won't have much use for it in your engineering classes. Okay, all right. You guys need more time? We're good to go? Okay, so this is the rise over run view of differentiation. Let's now look at a second way to view derivatives. And that says local linear approximations of functions. I want to do this somewhat carefully in the single variable case, because when we go to the case of multivariable functions, it'll be much easier if we do this just a little bit carefully. So here's the setting. We take a function on some interval. It's real valued, nothing complex, really. We got a point that's within this interval, and I'm making it an open interval, so it's not an endpoint where we can only take limits from one side or the other, okay? So just putting us in a simple setting. And suppose wish to approximate f near x0. So near will mean that in the limit, as we get closer and closer to x0, this approximation will get better and better. And we want to do it by f of x is approximately equal to y0 plus m times x minus x0. And this should work for x minus x0. So this is what near means. Okay, so we're going to approximate the function by a line. How do we choose the values of, how do we choose the values of Go through the line. There we go. So there's our local linear approximation. And my axis is leanings, like the leaning tower of Pisa, right? So that's f at x0. Okay? So if the function is supposed to be approximately equal to y0 plus m times f x0, so then f at x0 is approximately y0 plus m times x0 minus x0, so just plugging in x0. So the m drops out. And so y0 equals f of x0, okay? Makes sense. That's exactly how I drew my line going through the point. So it's at least the line is perfectly correct at the point x0. Okay, and then let's go back to, so this is now f of x0. And let's solve for m and see if we can recognize it. Okay, so we'll take m equals f of x minus f at x0 over x minus x0. And we want this to work for x close to x0. So we let x equal x0 plus h, absolute value of h, less than our number delta, whatever we were choosing for that. So for small. And then we see that we have m should satisfy, it's approximately equal to x0 plus h minus f at x0. And the denominator, when we subtract the h0, and then we see that as h goes to 0, this is the derivative at x0. Okay, so our linear approximation becomes y of x equals f at x0 plus f prime at x0 times x minus x0. And we'll just make that a definition. That is the linear approximation of f about, at, near, about x0. Okay, so it turns out this little simple idea of the linear approximation allows you to derive all of the differentiation rules known to mankind. So differentiation rules, they exist so that you can use our little small table of functions and then calculate derivatives of much more complicated functions. So all these are in the textbook. I'll just put them in the notes. Okay, so I'm just going to move it to a different page. So this one you will or have used on a daily basis. The derivative of sum is the sum of the derivatives. How do you differentiate the product of two functions? Quotient rule and the chain rule. So those are the main ones. And then the last important one is the power rule. So I won't even bother to write down the sum, the product rule, quotient rule, chain rule, and the power rule. And this one often causes challenges for young learners. You guys are more experienced, but and part of the problem with the chain rule, at least how it was taught to me, it was taught with the wrong notation, okay? If you use the right notation, the chain rule is just almost a triviality. So here's the generalized power rule, and we'll talk about that eventually. Okay, so these are the ones that all engineers are expected to be able to apply in their homeworks, okay, in daily conversation with other engineers. All of the others are just kind of optional. You'll see them every once in a while, but it's rare. And it rarely, even more rarely, comes up in a group setting. So it'll come up where you've got a chance to go quickly look on Wikipedia or look back in our textbook to get it. Okay, so what I want to talk about is where do these rules come from? Okay, and there's a really cool video that's linked in the textbook, and now I've got it linked in the lecture as well.
All in all, elementary core of calculus.
Okay, hold it. It's not coming through. Why is that? Source not high enough, maybe?
And work around them.
Yeah.
But those are topics for another video.
We'll talk about elementary functions. Okay, so that's a bust of Leibniz, okay? That's the dude Leibniz who has the prime notation. I mean, the df by dx notation.
All in all, the elementary core of calculus is this list of derivatives up there, plus the rules for finding.
Okay, so this is that table of all the derivatives that engineers need to know. And then these are the rules written underneath it. So let me go to full screen here, make it easier. Okay, so then there's the sum rule, difference is the same thing, the product rule, the ratio rule, and then hidden underneath the captions is the chain rule. Okay. Have you guys watched Mathologer videos before? Have you come across him? Probably not, okay. He's a German-American. You'll have to look at his t-shirt in a second. It's got the normal distribution on the top, and it has an abnormal distribution under it, okay? He's got hundreds of t-shirts that are all math-centric and very interesting, but he's really great at animating what would normally be a really tedious calculation in a way that you go, wow, I wish that would have been available in 1975 when I was going through calculus, okay? So if you haven't seen some of them, that's why I want you to see this.
There. As a challenge for those of you who know a little bit more, see what adjustments have to be made to what I said so far if we allow taking inverses of functions as the 6 operations to make new from old functions. Anyway, there's one more aspect to calculus that really makes it unusually user-friendly, and that aspect is notation, the nifty way in which we express calculus in symbols. This miracle notation was introduced by Gottfried Wilhelm Leibniz and was further streamlined over the years. This notation allows us to consider the core of calculus as a simple extension of school algebra. And in many ways, the incredible success of that 100-year-old calculus book lies in the way
You got to go back to the initial part of the video to see the 100-year-old calculus book.
And so to finish off,
I didn't think you would go out and buy one, so I didn't bother.
The basic elements of Leibniz notation and demonstrate its power by replicating and adding some nice twists to what's done in the book. Derive everything here from scratch in 5 minutes.
All of the rules in 5 minutes. We're not going to do all of them.
Calculating the derivative of a function at some point means calculating the slope of this touching line. At first glance, it's not clear how we can calculate the slope by looking at our function, but what's easy to calculate is the slope of a line that cuts the graph in a second point.
Secant.
And now, as you move the second point towards the first one like this, the slope of the line we're looking at approaches the slope of the touching line
abnormal
better.
Distribution.
In this way, we sneak up on the value of the slope that we're really interested in. As usual, we calculate the slope as rise over run. What's the run? Well, some x increment, and the rise, some f increment. As we push the x increment to 0, the f increment also goes to 0. The limiting slope is what we're after, and we write it as df dx. Now, in the first instance, that df dx is just an abbreviation for the limiting process I just described, and by themselves, the df at the top and the dx at the bottom don't appear to have lives of their own. However, the limiting process turns out to be such that to some extent we can actually calculate with these d increments very much as with numbers and algebraic variables. And by doing so, we can easily get all...
Okay, so he's going to show you in a very hopefully convincing way that if you just use the f prime notation, you can struggle for hours deriving all of the chain rule, etc. And if you use Leibniz's notation that comes from our intuitive notion of a derivative as rise over run, so delta f over delta x, and the limit as delta x becomes infinitesimally small, they just fall apart. So I want to see if you guys agree that it just falls apart.
It's natural to start with the simple sum rule, but I think it's much more fun and more impressive to take care of the more complicated product rule straight away. What's that derivative? Well, in terms of these weird d increments is this. Okay, and what is the increment df times g on top? Well, starting with the product f times g, as we increment x by dx, f will increment by df, and g will increment by dg. And so the orange increment is just the difference between these two products. Okay. But now it's just a matter of algebra autopilot. Expand the
You guys get that step? Just replacing f times g with f plus delta f and g plus delta g. And then to get the rise, you subtract off the original f times g. So that's the rise, and then the run stays dx, okay?
wonder.
Multiply it out, cancel. Break it up into sums. Ah, we got some
Now
leftover.
remember, in the limiting process, dg actually stands for the g increment going to 0. And so we can finish our calculation like this. Ta-da! I present to you the product rule. Very nice, isn't it? And now, as promised, I'll animate.
Sorry that my lectures are not animated and with music, okay, guys? You know, if I did that, you would be going like this, right? Ooh, we don't deserve you. But this guy's he wrote a really amazing set of software, apparently, for doing all these. So all of his videos have dancing formulas. Okay, so we're going to watch the chain rule, and then we're going to go through the chain rule steps ourselves. The product rule, that's derived in the textbook. The chain rule's in the textbook. The quotient rule is not, so that it can be on your homework, but you can look at him to get an idea for how to go about it, okay? Or you can just follow the same procedure that we will when we do the chain rule.
All the other rules of differential calculus and the derivatives of our atom functions just for you. Following this, I'll end with some quick snapshots of a couple of other instances of Leibniz notation working miracles that many of you will be familiar with, but that I won't get around to covering today. These snapshots also feature the second main ingredient of Leibniz notation, the integral sign, that elongated S, Leibniz's way to denote the antiderivative. Enjoy.
This is the one you guys do in your homework, okay? So just reminding you. You get x squared with the product rule. You know, overkill, but you can do it. Okay, we don't want to do those. Oh. Chain rule.
The derivative of one function subbed into another. What's that? Well, as the variable x changes by dx, the function g
That's the hardest one, right?
dg. And dg is equal to this, right? dx cancels out. dg is equal to dg. Now, as g changes by dg, the function f changes by df. And df, well, on the one hand, df is this. Obvious, right? Again, dg cancels. On the other hand, df is really the total change we're after. And now we just go on autopilot.
Yeah, I think
Very
that's
pretty,
almost
isn't it?
cheating. To me, it's not clear enough, doesn't give enough steps. So we're going to do it.
I really wish they showed this when I studied.
Sorry?
I really wish they showed this when I studied.
Yeah, so it's linked in the textbook, so it's real easy, or when you download the notes, you can watch the rest of it if you want. I mean, it's pretty cool. And it's just kind of showing that sometimes the way you write something down is important. You can use that to guide your thought process on getting at deeper facts in the subject. Okay, so that's all the second derivatives. Okay, so we're going to exploit this linearization. So you want to linearize a function about a point. You want to approximate it about a point. We take the value of the function at that point, and then the slope at that point times x minus x0. And that gives you this red line, exactly. You're used to writing y equals mx plus b, where you take x0 equals 0, but it's much easier to move that to the point x0. That's all it's doing. Okay, so objective. So you want to differentiate a composition of two functions. So what does that equal? So I'm going to do it just slightly different than the methodology did, but it's really the same thing. Okay, we're going to use the linear approximation and we're going to use the prime notation. You're going to see in the end, we're doing the same thing that Mathologer was doing. Whoops. Okay, Grizzle. Yeah, let's group all that and slide it down. I'll fix all this before I post. Come on. That's not what these guys signed up, is to watch you mismanipulate your we're almost there. Yay. Fresh ground. I should have just thrown it away and restarted, right? But I didn't. I'm about to. Come on, be nice. All I want is these young people to understand something better. Okay. I give up. I'll fix it later. Okay. D by dx, f of g of x equals. Okay. So, g of x plus h, by the linearization, it's approximately g of x plus g prime of x times h for absolute value of h small. F at y plus delta, it's f at the point y plus f prime at y times delta. Okay, so these are just the linear approximations. Ooh, how did you get changed to 2.5? That's my problem. Okay, just linear approximations. For us, y and delta are to be found. So what I'm going to do is write this derivation in the way that you would discover things on your own, not the way it would be written up as a proof in a math book. So proofs are written backwards. That's part of the reason you guys have trouble reading them. How much reading do you do backwards? I know at least one of our members can read left, right, it doesn't matter, okay? So that's already very good. Maybe there's more, okay? So this is the limit h goes to 0, f of g of x plus h minus f of g of x over h. So that's just the definition of the derivative. Okay, now for g of x plus h, I'm going to plug in its linear approximation. So f of, and I'll write it out so it's more distinct. Okay, so I use the linear approximation of g about x to evaluate g of x plus h for h small. Okay, so here's the cool thing. I can also do that for f. Here's my point y, and here's the point delta. So this will be y, and this will be delta. H goes to 0 implies delta goes to 0. Okay, so it's when h is small, delta is now a small perturbation about that. And so now we continue. Limit h goes to 0. And for f, we put in f at y, and y is g of x, plus f prime at y, that's g of x, okay, times y minus y0. Oh, which is the, excuse me, I've got this. Yeah, and then the y minus y0, that's the delta. Okay, so this goes f prime, and then this becomes g prime of x times h, that's delta. And then we have the minus f of g of x over h. So we've used our linear approximation twice. First to replace g, and then to evaluate f at g of x plus f prime at g of x times delta. And then just as in the mathologer things, those cancel. And this becomes limit h goes to 0 of f prime evaluated at g of x times g prime of x times h over h. And those cancel, and our limit is now trivial to evaluate. Okay, so that's the chain rule. You differentiate the outside function, plug the inside function in, and then multiply by the derivative of the inside function. That's the chain rule. Another way to write it, which was what was done with me, is you don't make it clear that f is really another variable y. So personally, I find this much less clear than the derivative of f evaluated at g of x, okay? To me, this is more clear, times the derivative of g. So it's cleaner than this evaluate at, etc. I don't know. What did they teach you in Math 115 or AP? First one or the second one? Both? First one, good. Okay, it's much easier. So things have, some small tiny bits of calculus have changed. Okay, so let's just do a few examples. So I don't know, just do a polynomial. So this is using two rules. The derivative of a sum is the sum of the derivatives, and it's using the power rule. So the 2 comes down, so we get 6, and then we subtract 1, that becomes 1. The 1 comes down, we subtract 1, that becomes 0, so the 2, and then this derivative is 0. So we get 6x plus 2. Almost too easy. Okay, so for this one, do you guys tend to use the quotient rule or the power rule? They didn't let me do that, okay? So things are better now than they were in 1975. Okay, so if you're doing it with the quotient rule, it's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. So that's the quotient rule. Okay, so that's 0. That becomes 1. And so this equals this equals 0 minus, what am I saying? Yeah, 0 minus 1 over x squared, and we get minus 1 over x squared. So that's the quotient rule. The generalized power rule is, yeah, it's much easier. So we write f of x equals x to the minus 1, and then f prime of x is minus 1 times x to the minus 1 minus 1 minus 1 x to the minus 2. Yeah, totally agree. It's so much easier. Okay, let's just do a few more, and then we're going to maybe do one just for fun. What if we have f of x equals cosine of e to the x squared plus 1? What are all of the differentiation rules that we need to apply here? Well, we've got a composition here. We've got another composition here, and we've got a power rule, okay? So it's chain rule plus power rule. Well, get that rid of that one. Okay. So cosine of y prime is equal to, we haven't derived that one, but it turns out to be minus sine of y. X squared plus 1 prime, we just get 2x e to the x squared plus 1 prime. So it's the derivative of e to the x, which is just e to the x, evaluated at the function. So we first just have this, and then times the derivative of x squared plus 1 prime. And so we end up with e to the x squared plus 1, and then times 2x. Right? Okay. Now I'm going to give you one and have you guys do it really quick as you can. Logarithm of 2 plus sine cubed of x plus x to power pi. Okay? See what you can get, Jason and Zoe and James. And it'll be a little bit painful to write that out, so it's up to you if you guys want to say, hey, I'm going to turn on my camera and I'm going to hold it up to the screen, okay? One more minute. I mean, it's about as gnarly as any engineer wants to do. So, without writing down all the intermediate steps. So, it's an f composed with g. So, what is the outside function? Driving, yeah, James, I wouldn't do this driving. I would recommend that, texting is already dangerous enough driving, but doing the chain rule driving, that's worse. So please do not do that while you're driving. Yeah, so the outside function is logarithm of x. So what's the derivative of log of x? Natural logarithm. 1 over x, okay. And so we put 1 over, and then we evaluate it at what's inside. So 1 over 2 plus sine cubed of x plus x to the pi. And then we have to multiply it, so I'm going to show this step. Whoops, x to the pi. Prime. Okay. Okay, so we differentiate the 2 and we get 0. We differentiate sine cubed. So how do we approach that? So it's a power. So the 3 comes down, and then we still have the sine squared. But it's a chain rule, so we need to differentiate sine. Everybody agree? Okay. Okay, so this is 0. This was 0 plus, and we got 3 sine squared of x times the derivative of sine of x, which is cosine of x. And then we apply the power rule here, right? And when we do that, the pi comes down. We have x to the pi minus 1. Yeah. So that's about as bizarre as they get. And just because one of the students last semester, who is a current IA, oh, thanks, Jason, yeah. Very good, and you even typed it out. I look spot on. Okay. One of the students was playing Stump the Chump with me, so I'm going to play Stump the Chump with you, okay? So what's good for the goose is good for the student gander, okay? How do you approach it? I mean, power rule is when that thing up there is like a constant, okay? So how do you approach it? Yeah, boy, key. Let me write this like this. F of x to power g of x is e to the natural log of f of x to the power. That looks really, really awkward. And the beautiful thing about logarithms, once again explained in chapter 1, is that the log of something to a power, the power just comes down in front. It's g of x, natural log. Okay. So now you've got an exponential, a product, and a chain rule. And so for us, we write f of x equals e to the log of x to power x equals e to the x times log of x. Now, quickly get the derivative for me. Looking pretty good, Jason. But I think you're missing one term. Take another quick look at it, okay? I think you're missing one term. So we only got 4 minutes. So we differentiate the exponential, which is just the same function, and we plug in. Then we have to do x logarithm of x prime. Okay, so that's just the chain rule. And then x log of x prime derivative of x is 1, so we get natural log of x by the product rule, and then we have x times the log of derivative log of x, which is 1 over x, and so that's natural log of x plus 1. And this, that's just the original x to power x. This is just because somebody played Stump the Chump with me and they were pretty sure I couldn't do it, okay? So that's the only reason we're doing it. It's not like it's an important engineering thing. So you get x to the x, and then you get natural log of x plus 1. So that was the plus 1 method. Yep, now you got it. You corrected it. Perfect. Okay.